Unsigned decimal representation are special ways to represent or write unsigned integers using a base 10 system. We're going to talk a lot about that in this lesson and continue to expand on it in future lessons. To start this conversation, let's go back to our table of popular number systems. We're going to run through each of these individually and then talk about how decimal representations relate to them. The first set of numbers that is very popular in mathematics is the natural numbers. That's written in blackboard N notation. When you see these double legs on a mathematical symbol, that's known as blackboard notation because sometime way back in history, there was something called a blackboard where you'd write in chalk. And to highlight special sets of numbers, old mathematicians would write two lines on the blackboard to distinguish it from a normal letter. So when you see blackboard N notation, that means the natural numbers, and it's distinguished from a capital N because it has two diagonal marks rather than just one for a capital number. The natural number includes all positive counting numbers or all positive whole numbers, 1, 2, 3, 4, all the way up to infinity. In conventional mathematics, we actually go from the natural numbers up to the integers. The integers is labeled with blackboard Z notation, so it's a Z where the diagonal is double lined. Those integers include all positive, negative, and zero whole numbers. The way I like to write this best is 0, -1, 1, -2, 2, -3, 3. So this actually tells us that all 0, negative, and positive whole counting numbers are in the set of integers. From the standpoint of computer science, though, we're going to call these the signed integers because they include both positive and negative signs. There's a distinction between negative and positive in this set of integers. We're going to compare that with what we call the unsigned integers, and I'm going to include new notation in my class that I did not see in my entire 10 years of undergraduate and graduate education. We're going to use uppercase blackboard U for unsigned integers. And the reason that this is useful is a lot of mathematicians refuse to include 0 in the natural numbers. But in this class on coding and MATLAB, we will actually need the set of non-negative counting numbers. Computer scientists call those unsigned integers. So we're going to use the capital U and just define our own set using blackboard U notation. So anytime you see blackboard U, we're going to see that as the set 0, 1, 2, 3, 4, all the way up to infinity. It's the non-negative counting numbers, or the natural numbers plus 0. Those three sets, the natural numbers, the unsigned integers, and the signed integers, are the set of integers that we're going to focus on in this course. We are also going to talk about what we know as rational numbers. Those are denoted using blackboard Q notation. That's what we see right here on screen. The set of rational numbers is the set of ratios between integers. So it's the set of all P divided by Q with two conditions on those two numbers P and Q. Specifically, P and Q in this formulation are integers, and the denominator Q can never equal 0. So we're going to actually run through all possible integer fractions where the denominator is non-zero. That's the set of what we call rational numbers. There's also a larger set known as the real numbers. The symbol that we use to represent real numbers is blackboard R notation. In this introduction to MATLAB, we are not going to go through the construction of the real numbers, so we're not going to give a set theoretic definition of this. Just suffice it to say that anywhere we see blackboard R notation, that is the set of all x, such that x is a real number. The final very popular number set that we see in mathematics and is also very relevant to MATLAB coding is the set of complex numbers. The complex numbers are combinations a plus b times I, where a and b are any real numbers and I is the square root of -1. MATLAB does actually allow us to store complex numbers, and specifically I is set aside as the square root of -1. We're not going to focus heavily on that in this course since this is an introduction and that gets into more complex applications. What I will say is in our discussion of numeric data classes in MATLAB, these first 5 sets, the natural numbers, the unsigned integers, the signed integers, the rational numbers, and the real numbers, are going to come in very helpful as we try to understand how MATLAB is storing numeric variables within its memory system. What are the maps used to encode numeric variables? Once we understand that information, we'll have a much better idea of the accuracies and inaccuracies, in other words, the features of MATLAB numeric data, and how we can take advantage of that while we write computational code. Let's jump right into the heart of the content of this video by exploring decimal representation of unsigned integer. Unsigned integers are mathematical ideas having to do with quantities that exist as whole numbers. Decimal representations are a way that we express and represent the value of those numbers in a base 10 counting system. One of the core concepts in representing numbers using a decimal system is what we call the set D, the set of decimal digits. In other words, each decimal digit is going to be chosen from this set D, and there are only 10 choices that a single decimal digit can take on. Those include the number 0, 1, 2, 3, 4, all the way up to the number 9. We're going to come back to this over and over and over again when choosing the values of each digit in a decimal representation of a number. Each digit can only take on one of 10 values because decimal representations represent ideas in base 10. One of the best ways to get our head around what decimal representations are and how they work are to work through specific examples. So in this case, we're going to start with our first example, which is an unsigned decimal integer represented with one decimal digit. We'll start with a number y1, which is in the set of unsigned integers. That is our Blackboard U notation. And we'll say that y1 is equal to the number 9. The moment we write y1 equals 9, this actually has very special meaning within our decimal system. Specifically, this number is represented using one decimal digit. And specifically, we can see the first decimal digit in this representation is the number 9. But when we're thinking about the value represented by that number, that is represented with respect to what we call base 10 representation. So specifically, 9 is actually 9 times the number 1. And the number 1 is really special because that's actually 9 times 10 to the 0. Remember, 10 to the 0 is 1. So when we say that y is equal to 9, what we're saying is when we're counting groups of size 10, there are 9 groups of size 10 associated with the power of 0. The moment that we start identifying powers of 0, we're going to call that the position value for each individual digit. So another way to say that y1 is equal to 9 is to say y1 is 9 times 10 to the 0, where the scalar coefficient 9 is matched with position 0 on base 10. Let's go on to a second example to explore further what we mean by this base 10 representation. So we're going to take another unsigned integer, this time we'll call it y2, and we'll set y2 equal to the decimal representation where we have a decimal digit 1 immediately followed by the decimal digit 3. In this case, let's go ahead and count the digits. Notice that we have digit number 1, digit number 2. So there are 2 digits in this decimal representation. And then what we actually mean when we say this number is 13 or 1 10 and 3 ones is here, this counts the number of tens. Well, how many tens are there? There's one of them. On the other hand, the digit 3 represents the number of ones there are. Well, how many ones are there? There's 3 of them. But here's a claim, counting the number of tens and counting the number of ones is equivalent to actually tracking the number of powers of 10 starting at power 0 and moving upward. So in other words, when we say the number 13, this is 1 times 10 to the first plus 3 times 10 to the 0. The moment that we see it this way, we can refer to these as the position numbers. So when we say that y is equal to 1, 3, what we really mean is y is equal to d1 times 10 to the 1 plus d0 times 10 to the 0. This digit d1 in this case is 1, d0 is 3, and what we mean is this is the digit corresponding to the power of 10 where the value in the power is 1. So d sub 1 is multiplied by 10 to the 1. D sub 0 is multiplied by 10 to the 0. What is the value of d sub 1 in this specific number? It's 1. What's the value of d sub 0 in this specific number? It's 3. In other words, 1 represents the number of 10 to the first powers we have, and 3 represents the number of 10 to the 0th powers that we have. Let's move on to yet a third example. In this case, we're going to have a 3 decimal digit representation of an unsigned integer. We'll call that y3, and that's in the set Blackboard U. In this case, this 3 decimal digit representation is going to lead with the number 1. We're going to write a decimal digit 0 followed by a decimal digit 0. Of course, we would call that 100. But my claim is that underneath that representation is something much more interesting going on. Specifically, this number represents that we have 1 group of 100, 0 groups of 10, and 0 groups of 1. But of course, when we're thinking about these digits, the first digit on the least significant portion, digit number 2 and digit number 3, those digits really represent multiples of the corresponding powers of 10. So when we write 1, 0, 0, what we mean is 1 times 10 squared plus 0 times 10 to the first plus 0 times 10 to the 0. Well, in decimal representation, we would say that that power represents the position value, the power of the base, and we're going to index each decimal digit using that position value. So d sub 2 times 10 squared, what is d sub 2 in this case? Well, it must be 1 because 100 has 1 group of 10 squared. Plus d sub 1 times 10 to the first, notice the 1 on the subscript matches the 1 in the power. d1 in this situation is really telling us how many groups of size 10 do we have, or 10 to the 1. How many groups of size 10 do we have in 100? We have 0. D0 is also 0 because there are no 1s. There are no 10 to the 0 groups in this number. In other words, 100 is equivalent to this decimal representation where each decimal digit represents a scalar factor in front of the corresponding power of base 10. That's why we call this a decimal system. Deci represents 10. Fun thing about digits is this is actually Latin for fingers, and it is not a far jump, skip, and a hop away for the hypothesis that the reason that we think about digits as storing information is we've got these little spirit fingers. There are 10 of them. So each digit represents information that we could store on our hands. The major point of this representation is really to make the connection between how we represent numbers and the corresponding ideas used to construct the value of that representation. This might seem like overkill in this example, but we are about to, in the next 2 videos, look at completely different number systems for representing numbers. We're going to look at binary representations. Binary means 2, base 2. So instead of representing it base 10, we're going to represent all of our numbers base 2. We're also going to look at hexadecimal. Hex means 6, decimal means 10. That's actually 16, not 60, so 1, 6. We're also going to look at representing numbers where the base is 16 rather than 10. So the reason that we're discovering or rediscovering the decimal representation in the abstract format is we're going to use this as a foundation and then simply change the base from instead of 10, 2, or instead of 10, 16. Then we're going to explore what would that actually mean. The claim is that MATLAB is doing this type of encoding every time we're putting numbers into MATLAB. The reason that we're going through this in a discussion rather than in MATLAB code is this all predates MATLAB's existence. Much of the work on unsigned integers, signed integers, and floating point data before MATLAB was ever created and MathWorks was a company. So in order to understand what MATLAB is doing, we should really try to understand what's going on with number systems and representations so that we can map that understanding back into the computer programming language and then fully take advantage of the features of the numeric data encoding. I'll do one more example in this video for you, and then I'm going to give you a challenge to do your own example. In this case, we're looking at yet a 4th unsigned integer. In this case, we're going to use 4 decimal digits to encode that. That unsigned integer is going to be represented by the string of decimal digits, 8191. In English, of course, we would say 8,191. But the claim is we're going to interpret what this means based on the decimal representation. Notice there are 1, 2, 3, 4 different digits, and we can count those digits as well as interpret what they mean. So when I say 8191, what I mean is I have 8 groups of 1,000 plus 1 group of 100 plus 9 groups of 10 plus one group of 1, each digit represents the corresponding number of size, where the placements of the digits tell us the position that those numbers are corresponding to. When I translate that into a decimal representation, what I mean is that each group of 1,000, that's 10 to the third. So this is in the third position in our decimal representation. 8 times 10 to the third, that gives me 8,000. The second position is the position aligned with 10 squared. So that's 1 times 10 squared, which is of course one group of 100. The first position is aligned with 10 to the first powers. How many groups of 10 to the first powers do I have? Well, I have 9 of those. In other words, that's 9 times 10 to the first. And then I have one group of 10 to the 0, or I just have 1, 1. I can abstract away from this exact value to a more general format where I write this set of numbers as d3 times 10 to the third plus d2 times 10 squared plus d1 times 10 to the first plus d0 times 10 to the 0. The letter D is used to represent the idea that we're in the decimal system. Decimal means that I'm choosing each of those values of D from my decimal numbers. In other words, I can only have 10 choices for each of these D values, either 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. In this specific case, we know that D3 is 8, D2 is 1, D1 is 9, and D0 is 1. The subscript on each of those decimal digits represents the power of 10 that that digit is associated with. When we're writing this representation, the position of each digit in that string of decimal digit tells us the corresponding power that we're going to map that digit to. Let's explore this a little bit deeper. Remember that we said that the position number of a specific digit corresponded with the power of 10. Let's formalize this with a definition, which is called the position of a decimal digit. The position of a decimal digit is the value of the power of base 10 associated with that digit in our decimal representation. So when we say D sub 0, digit D0 is multiplied by 10 to the 0, and that's exactly what we see here. When I say 8191, that last one tells me the number of ones that I have in my number. In other words, the number of 10 to the zeros. Thus, we say that that digit is labeled as D sub 0 because the index right there maps to the power of 10 in that decimal representation. Similarly, we say that the digit D sub 1, D1, the index on that is 1 because that is really multiplied by 10 to the first. In other words, D1, the value 9 in this particular representation, that is right here, tells us the number of tens in this decimal number. We can generalize that and say that the digit D sub k is going to be multiplied by 10 to the k, or in other words, D sub k counts the groups of size 10 to the k. Now, this is really interesting because notice the number that we have on screen, the 8191, that has 4 decimal digits. Here they are, 1, 2, 3, 4. But notice that the largest digit actually has subscript 3. And the reason that that is the least significant digit, the value of 1, actually corresponds to D sub 0, or another way to say that, that least significant digit counts the number of 10 to the 0 groups. Once we've defined this position of a decimal digit accordingly, we can actually look back at our 4 examples that we've done so far and start making a connection with the number of decimal digits and the corresponding position used in each of those. So when we had 1 decimal digit, we were only at D sub 0. In other words, we only needed D sub 0 corresponding with 10 to the 0. When we had 2 decimal digits, the largest position that we touched was D sub 1. So this string would be D1, D0. And when we're at 3 decimal digits, we actually go up to D2. So notice 1 goes to 0, 2 goes to 1, 3 goes to 2. The 4th example where we had 4 decimal digits, we only got up to the position in the 3rd place, or the 3rd power of 10. So 4 goes to 3. Do you see a relationship between the number of digits and the corresponding number of positions that we take advantage of in our unsigned decimal representation? Let's see if you got it. For a 5-digit representation, how many positions would we take advantage of? Yep, you got it. We would take advantage of 4 positions. So if I tell you that I have an n-digit decimal number, the largest power of 10 is going to be n minus 1. The moment we come to that realization, we can define what we call the general form for an unsigned decimal representation. If we say that y is an element of the unsigned integers, remember those are the non-negative counting numbers, we say that an n-digit decimal representation of y is given as y equal to d sub n minus 1 followed by d sub n minus 2 all the way down to d2, d1, d0, where each of these is a decimal digit in our set of decimal integers. In other words, each of these can be one of 10 numbers, either 0, 1, all the way to 9. Well, what did that mean? Each of these digits is going to be paired with its corresponding power of 10. And specifically, the value of the index on each of these digits corresponds with the power in the exponent of base 10. So d sub n minus 1 pairs with 10 to the n minus 1. D sub n minus 2 pairs with 10 to the n minus 2. We can go all the way down. D sub 2 pairs with 10 squared, D1 pairs with 10 to the 1, and D0 pairs with 10 to the 0. Remember, this is an n-digit representation. On cursory look, it's a little bit strange that the most significant digit has a subscript n minus 1. But if we look a little deeper, remember n digits means that we have a string of n decimal digits. Here, our numbering system is not starting with 1. It's starting with 0 because the least significant digit counts the number of 10 to the 0 groups that I have. A normal human being would say that's the number of ones that I have. Well, if I start at 0 and I have n of them, I can go no higher than n minus 1, and that's where that representation kind of comes from. And we saw that in the table. If I have 4 digits, the highest power of 10 that I'll hit is 10 to the 3. If I have 6 digits, the highest power of 10 is 10 to the 5. We can write that in summation notation by simply just combining all of those with the summand. So we start at the least significant bit, which is D0. That counts the number of 10 to the zeros. We go up to I equal 1, that counts the number of tens. I equal 2 counts the number of hundreds. I equal 3 counts the number of thousands. And we continue all the way till we get to n minus 1. Notice each one of those digits has to be chosen from our set of decimal digits, 0 all the way up through 9. The last thing that we'll formalize is that when we say the value of the index on our decimal digits, what we mean in this general representation, when we look at d sub k, remember, D represents the idea that we're capturing information with respect to the decimal system. Decimal means 10. So this is a base 10 representation. Anytime we see D, we're thinking decimal base 10. Then when we look at the subscript, we call those indices. Remember, the value of the index matches exactly the position number of that particular digit. Position numbers are another way to say the power on base 10 corresponding with that digit in the representation. So when I say D2, the position number is 2, which means D2 is going to be paired with 10 squared in my representation. Subscripted index values on digits in Y equal the position number for that digit. In other words, the index on each digit matches the power of 10 associated with that digit. That is a habit that we're going to carry forward in all of the representation that we work with in this unit. Because our math education system in the United States introduces decimal representations at such a young age, many students develop real fluency with decimal numbers without thinking deeply about what those decimal numbers actually mean. However, in order to fully understand what MATLAB is doing with its different numerical data class, we actually have to develop conscious competencies around number systems and understand how those map into data classes in MATLAB. With that in mind, let's filter one of the examples that we looked at in decimal representation through a concept of MATLAB coding, and specifically that's focused on MATLAB as an array-based language. I'm going to claim that decimal representations at their heart are actually vectors of decimal digits. So what I mean by this is, let's look at the fourth example that we were considering. In that example, we were looking at the number y4, which was 8191. We're going to create a decimal vector, and we're going to call that a row vector. each entry in that vector has to be from the decimal digits 0, 1, 2, 3, all the way to 9. My claim here is that this representation actually represents an idea that can be stored in vector form, and in fact, it is a vector. This actually stores vector-based information. In order to make that example explicit and to find a vector that is equivalent to this, we have to make a decision. Are we going to count up or down? And to this, I'm going to refer to one of my favorite hip hop artists, Drake, and he says we start at the bottom and now we're here. So I'm going to start at the lowest bit. Let's say that the first entry of our vector is 1, the second entry is 9, the third entry is 1, and the fourth entry is 8. The claim that we're going to make is that these values, these digits, only make sense in the concept of position number. Or another way to say that is, decimal digits only store information when we think about those as associated with base 10. Well, let's go ahead and create a vector p that has all the bases of 10 associated with each of these decimal digits. So remember, we can do that by doing 10 times 1s. Well, this one is going to be a 1 by 4. And then we're going to actually take powers of 10. Which powers of 10 we're going to take? We're going to take 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3. So in other words, in our exponent, we're going to start at 0, go up by 1, and go to 3. Let's go ahead and put a semicolon here, and now we'll run this. So look, D has the individual powers, and then P has the corresponding powers of 10. Oh, no, it doesn't. Of course it doesn't, because MATLAB works on operator precedence. Exponentiation has higher precedence than multiplication. So I actually need to tell MATLAB, please first create the vector of 10s, then do the component-wise powers. Let's clear the command window and try that one more time. P now stores the corresponding powers. Now what we're going to do is we're going to create an approximation, a calculation-based mechanism to try to get this number based on its representation. In order to do this, let's create a row partitioned matrix. So the first row is going to be D, and then the second row is going to be P. We'll go ahead and delete X4, which is going to be our approximation for now, and we'll run this. So notice what we're saying here is that this vector of decimal digits, each of the values is corresponding with the power of 10 that we want to multiply by. So in this case, what we're going to do is let's initialize our scalar, which is going to be X4. Then we're going to drop into a for loop, and we're going to go over all possible digits. Well, how many digits do we have? We have 1, 2, 3, 4. So I'm going to say let I go from 1 to 4, and we'll end our for loop. And then each value of x4 is going to be updated by the previous value of x4 plus d sub I times the corresponding p sub I. In this for loop, we've started with the value x4 equals 0. So what we're going to do is in the first iteration, when I is 1, the value of x4 is going to be 0. Then we're going to take d1 times p1, which is 1. So 0 plus 1 is 1. We'll store that in x4. I is going to be updated to 2. Then we're going to go in here. This thing started at 1. Then I'm going to say D2 is 9, P2 is 10. So 9 times 10 is 90. Remember, the previous value of x4 was 1. 1 plus 90 is 91. Then we'll store that in x4. We'll update this. Go to the third value. That's going to be 1 times 100. So this is going to be 100 plus 91. So that's 191. And then the last one is going to be 8,000. So 8,000 plus 191 is 8,191. Let's go ahead and run this code. We'll delete that and then run. Notice we can actually look at Y4, which is 891, X4, which is 891. Classic numerical analyst says that my approximation is going to be equal to my actual number when the difference between the two of those is 0. So let's go ahead and look at Y4 minus X4, and we'll call that an error. So if my error is 0, this approximation is going to be exactly equal to that. And then what we'll do is we'll throw an absolute value on that because it could be negative or positive. So the claim is this function will produce my decimal representation exactly if my error between my original number and my calculated number is 0. Let's go ahead and suppress the output inside the for loop, run this again. Notice the error is 0, which says we've actually created a for loop representation to translate our decimal into its actual value. And from that standpoint, I would claim that all decimal numbers are actually vectors in disguise. Each individual digit tells us the power of 10, And then we will see this as something called a dot product. This is a for loop representation of a dot product. But indeed, if I were to actually look at D and P, there's something called a dot product representation, which is if I take D times P transpose, I get the exact same value because literally all I'm doing is pairing those off individually. Now, of course, some of you would say, hey, Jeff, this was really, really weird. You stored this decimal representation in the exact opposite order. And you're probably right. The claim is, of course, I could actually represent this as 8191. In that situation, instead of starting at 0 and going up to 3, I could start at 3, go down by -1, and go down to 0. If I reran this code, notice my error is still 0 because D now is represented in the way that most numbers are reported, and then P has this descending power structure that allows to capture the way that we write that as expected. All of this work is to set the foundation for binary representations. In other words, what would happen if instead of using each of these individual digits in the decimal set, we limited those to either being 0 or 1. In other words, it's a binary set. There are only two choices. And then instead of powers of 10, we chose powers of 2. So how would our representation change if we represented numbers using a binary system rather than a decimal system? That's the exact question we're going to answer in our next video. I always welcome your questions, comments, and feedback in the comment section below. Every time you provide me feedback, I grow as a content creator. Thank you so much for your attention, and I'll see you in the next video.